A list of 10 billion items crashes your program. A generator of 10 billion items uses almost no RAM. I am Ahaz. Today in episode 27, Generators and Iterators, you will learn exactly how lazy evaluation works and why it matters. We will cover the difference between a list and a generator expression and why that difference is 840 times more memory, the yield keyword, how it pauses a function mid-execution and resumes it on the next call to next, the full Iterator Protocol, dunder iter and dunder next, which is how Python for loop actually works under the hood, send, two-way communication that passes values back into a generator at the exact yield point, yield from delegating entirely to a sub, generator in one line, and the itertools module, a toolkit of lazy combinators that handle ILS, chain, cycle, accumulate, and take a while without reinventing them. We will finish by building a lazy CSV pipeline that processes any file size with constant RAM. Let's go. The single most important difference between a list and a generator is when the values are computed. Look at the two panels. On the left, a list comprehension. Square brackets evaluate every element right now, store them all in memory simultaneously, and return the whole list. For 10,000 elements, that is 87,000 bytes. On the right, a generator expression. Parentheses create a generator object. No values are computed yet. Sys.getSize of reports only 104 bytes, 840 times less than the list. Values are produced one at a time, on demand, as you iterate. This is called lazy evaluation, and it is why you can iterate over 10 billion items without running out of memory. The rule is simple. If you need all values at once, use a list. If you process values one by one, use a generator. A generator function looks like a normal function, but it contains at least one yield statement. Look at the code. Countdown takes in. When you call it, Python does not execute any of the body. It immediately returns a generator object. When you call next on that generator, execution starts, runs until the first yield, pauses there, and returns the yielded value. Here, 3. The function's local variables, n equals 3, are frozen in place. The next call to next resumes from exactly that yield statement, decrements n, loops back, hits yield again, and returns 2. When n reaches 0, the while loop exits, the function returns normally, and Python raises stop iteration to signal that iteration is done. A for loop calls next automatically and catches stop iteration for you, which is why for val and countdown works without any manual next calls. Yield is the keyword that turns a plain function into a generator. Python's for loop does not know anything about lists, generators, or files specifically. It only knows the Iterator Protocol, two methods, dunder iter and dunder next. Look at the code. Our counter class stores a current count in and a stop value. Dunder iter returns self. This tells Python that this object is its own iterator. Dunder next is where the real logic lives. If n has reached stop, it raises stop iteration. That is the signal to any for loop or next call that there are no more values. Otherwise, it increments n and returns it. Calling list on counter of 4 gives us 1, 2, 3, 4. Any object that defines these two methods works everywhere an iterable is expected, for loops, list, zip, map, and every itertools function. Generator functions implement this protocol automatically. Python builds dunder iter and dunder next for you. Generators are not just one-directional. You can send a value back into a generator at the yield point. Look at the code. Running _average is an infinite generator that maintains a running average. The yield expression appears on the right side of an assignment. Value equals yield total divided by count. This does two things at once. It sends the current average out to the caller, and it waits to receive the next value in. Before you can send anything, you must prime the generator with a bare call to next. This advances execution to the first yield. Now average.send of 10 resumes execution, assigns 10 to value, updates total and count, and yields back the new average, 10.0. Average.send of 20 yields 15.0. Average send of 30 yields 20.0. Average.close sends a generator exit into the generator, which causes it to stop. Send enables two-way pipelines, push data in, pull results out, one yield at a time. When you need to delegate all iteration from one generator to another, yield from is the right tool. Look at the two panels. On the left, the manual way. We loop over iterable A, yield each item, then loop over B, yield each item, 6 lines. On the right, yield from A, then yield from B. 2 lines, same result. But yield from does more than save typing. It transparently passes send calls, throw calls, and close calls through to the inner generator. So two-way communication works through the delegation chain. Without yield from, you would have to manually forward every send and throw yourself. Yield from is also what makes Essentio work under the hood. Async, def, and await are built on top of this exact mechanism. Use yield from whenever you want one generator to fully hand off to another. Python's Itertools module is a collection of fast, memory-efficient iterator building blocks. All of them are lazy. They produce values on demand. Look at the code. ILIS is a lazy slice. List of ILIS of range 1 million. 5 gives you the first 5 elements without materializing the million element range. Chain glues multiple iterables together end to end. Cycle repeats an iterable forever, useful for round-robin scheduling. Accumulate produces a running total. List of accumulate of 1, 2, 3 forgives 1, 3, 6, 10. Take while yields items as long as a predicate is true, then stops. So take while lambda x less than 4 over 1 through 5 gives 1, 2, 3. These 5 functions cover the majority of lazy iteration patterns you will encounter in real code. Import itertools. Do not reinvent it. Our mini project. A lazy CSV pipeline that processes files of any size with constant RAM. Look at the code. Read_rows is a generator function. It opens the file, skips the header with next of f, and yields each data row 1 at a time as a split list. Parse_floats is another generator. It takes the stream of rows, extracts the chosen column, converts it to float, and yields it, silently skipping any row that cannot be converted. To build the pipeline, we call read_rows on our file, pass the result to parse_floats, then call sum on the result. At no point do we load the entire file into memory. Each generator yields one value, passes it to the next stage, and immediately throws it away. This pipeline uses the same RAM whether the file has 1,000 rows or 1 billion. That is the power of chain generators. Your challenge: build 3 generators from scratch. Step 1. Write a Fibonacci generator that yields each Fibonacci number indefinitely. No list, no recursion, just 2 variables and yield. Step 2. Write a running_min generator that takes any iterable and yields the smallest value seen so far after each new element. Step 3. Use itertools.ilis to print the first 20 Fibonacci numbers from your Step 1 generator. Step 4. Build a lazy log line parser. Given a log file, yield only lines that contain the word error. Step 5. Compare memory. Measure sys.getSize of on a list of the first 10,000 Fibonacci numbers versus the generator object. Paste your generators and the memory comparison in the comments. I read every single one. Let's recap what you learned today. A generator expression uses 840 times less RAM than an equivalent list comprehension because it produces values lazily, one at a time. A generator function contains yield. Calling it returns a generator object and next resumes it from exactly where it paused. The Iterator Protocol is dunder iter and dunder next. Any object that defines these 2 methods works in a for loop, zip, map, and every itertools function. Send passes a value back into the generator at the yield point, enabling two-way pipelines. Close sends generator exit and triggers cleanup. Yield from delegates all iteration to a subgenerator transparently. Send, throw, and close all pass through. Itertools provides ILIS, chain, cycle, accumulate, and take while, all lazy, all memory efficient. And the mini project showed how to chain generators into a pipeline that handles any file size with constant RAM. Next episode, metaclasses and dunner init_subclass. how Python builds classes, and how you can customize that process. Subscribe so you don't miss it. See you tomorrow. Generators and iterators. Mastered. Your code now streams data lazily. Constant RAM, infinite scale. Subscribe for the next episode. Drop your Fibonacci generator in the comments. I am Mahaz. See you in episode 28.